Yeah, okay, welcome back. Let's continue the 2D simulation. Yeah, today we are going to discuss about the rectangular element. So compared to the CST element, rectangular element has a 4 node, so that they have one more node, so that displacement field can be slightly it's defined using those kind of way. Yeah, in the previous triangle element expressed looks like this. However, in here, so rectangular element, we have have one more nonlinear terms. So in four node element, we have one more degree of freedom, so that each direction have a 4 degree of freedom, so total 8 degree of freedom, so that we have opportunity to have one more coefficient, so that Q4 triangle element, we usually call it the Q4 element, so that so they will have a slightly difference compared to the triangle element today. So we are going to discuss about the more detail about rectangular element. So this rectangular element has some pros and also or con. First, disadvantages is compared to the triangle element. They have some slightly nonlinear displacement, so that that result some difficult to the integration in the local stability matrices. So or they need one more some nodal point, and then compared to the disadvantages, we have two advantages. First advantages is if we can interpolate more accurately inside element. In the previous triangle element, the interpolation function is a simple linear interpolation, so that the result is simply mean values depending on the shapes. However, in the rectangular element, they have some nonlinear interpolation function. They have some more accurate value inside element, and also then they will can return to the more accurate stress and strain field. In the triangle element, the stress and strain is simply determined by constant. However, in the rectangular element, they defined by as function of the x and y, so that we can measure the more varies result compared to the triangle element. And also due to those kind of reason, we can use a small number of the element compared to the triangle element. Those kind of reason I'm going to explain the next 50 slide. So that let's check about the rectangular element more detailed. So in the rectangular element, we have 4 nodal points. Each node has 2 degree of freedom, so the total degree of freedom is 8 degree of freedom. So total displacement can has a 8 by 1 vector form. So so we are going to set our displacement field looks like this, and with the x and y linear interpolation with some combined complex term, so that and each nodal point position are predefined, so that we can apply our boundary condition of the u1 and u2, u3, u4, and v1, v2, v3, v4 as a boundary condition. We can summarize our displacement field, and looks like this. And here displacement field can be discretized using the interpolation function. So each u n1, n2, n3, n4 can be say that looks like this. Yeah, and also v displacement also same form of the interpolation function. So yeah, maybe displacement function can be expressed by shape function. Each shape function has those kind of function. Each shape function has a function of the n, x, and y. Similarly, in the triangle element, however, they have some nonlinear x and y conjugate terms. So anyway, also next, let's define the strain. Strain is a derivative of displacement function, so that we already know that those kind of things. Each strain field can be expressed looks like this in the previous slide. U is a function of the a1, a2x, a3y, and a4, and x and y. In here, the a2 and a4 and a y only relate to the x independent variable. Thus, strain in the x direction is a2 plus a4y, and the strain y a7 plus a8 axis. So that and strain field and looks like this. Compared to the triangle element, can you remember the strain in the x direction? It may be beta 1 in the triangle element, and also y is a gamma 1 or gamma I or beta I and gamma y depending on the coordination. So anyway, these values are constant, but in here the strains are also function of the x and y independent variable, so that this is a slight difference. So anyway, finally we obtain, we should calculate the gradient matrices. Each gradient matrices can be calculated looks like this, and y, and then conjugate term with, and then we have m4 and x equal to 0, so the size of the 3 by 8 matrices, so that the result is looks like this. And then in the triangle element, the B matrices matrices element were constant, but here the y and x are remains. That means that gradient matrix in the triangle rectangular element is a function of the x and y. Same manner. So that, and here, so that our general stiffness matrix equation can be expressed looks like this. B transpose and multiplication elastic stiffness matrices, and B matrices, and thickness, and the cross section integration on the whole domains or surfaces. So that, but we have a specific region. The looks like this, from minus b and b and minus h to the h. So that, but here, so in the previous triangle element, this inside equation can be easily escaped from this integration equation. It is because that all values are constant, but in here the gradient matrix is a function of the x and y, so we should perform the integration in here. So it will makes burden to you, maybe compute. But in this stages, how can we computer integrate this equation? If you run about the numerical method in the 2 years ago, I think that one suggestion is Gaussian quadrature. So in the FEM method, when you use some nonlinear element, actually triangle element also use a numerical integration. However, in the previous lecture, I skipped this numerical integration. However, we need some numerical integration technique, so that most common method is a Gaussian quadrature method. So next lecture, I'm going to introduce briefly of the Gaussian quadrature in the one-dimensional cases, so that, and then if you guys can do the numerical integration, we can easily obtain the local steepness matrices anyway. But similarly, external forces can be expressed, and then finally, we obtain the local steepness equation. And then, so I prepared some example, to compare to the CST element and QPO element. This QPO, rectangular element has 8 by 3 by 8 and 8 by 1 displacement field. It is because that rectangular element 4 node, each node has a 2 degree of freedom, so that the result, calculated result, can you guess it? So you can calculate the matrix multiplication, final result 3 by 1 vector. And then CST element, although gradient matrix size of the 3 by 6, but after the multiplying the matrix calculation can reach the 3 by 1 vector, same form. And also I performed the same model structure. This beam structure fixed on the wall. We apply the external forces end of the beam in the -y directions. So the result is can be expressed, looks like this. This is a result of the stress in the x direction. Here, triangle element shows a distinguished color. It is because that each element stress values, each element we have a stress x and x direction, stress y, y, and shear stress, x, y. They always constant in the inside full domain. However, in the rectangular element, the stress is a function of the x and y. So that means that stress can varies inside element. So this CST element can only suggest specific distinguished values. However, QPO element shows some gradient or variation the values in stress or strain inside element, so QPO element has some beneficial to interpolate result. Actually, exact values only calculated at nodal point, at each nodal point, so that the inside element the values are interpolated. Displacement field are interpolated, but the strain values or stress are calculated by some our Hooke's law relationship, so that in here we use a linear interpolation function, so the strain and stress calculated values are always constant, but in the triangle element they show some variation inside the element, so that with the small number of the element, the result more accurate or similar than CST element. So next time we are going to, I think that I already discussed about these issues in the COMSOL simulation. So I think that why the different element shows a different result. So there are some reference about the result, so that although we use a small, let's compare to the accuracy. So where is the QPO element? We use a 6 node element. Yeah, if we same number of the node, however, degree of freedom also similar, but the displacement result are quite different. So that yeah, the stress tensor stresses are quite different. However, when you increase the number of the degree of freedom, that means that number of the element, so that solution can be saturated. But yeah, there are no big difference. However, in the triangle element, there are big changes when you increase the number of the element. It is because that triangle element cannot suggest accurate value than cupo element. So there are many numerical issues on the triangle element. However, when you use a more complex geometry, so to discretizing this element, so rectangular element you cannot make well matched shapes, so that a triangle element more easier to represent the complex geometries. So generally you guys can use a triangle element, but if you have opportunity to use a triangle element depending your geometry, I strongly suggest to use a rectangular element first. So this is our result. That's why we use a cupo element. So this is a summary of the lecture 6. So in the two-dimensional spaces, so that we learned about how to derive our local stiffness equation based on the plane stress and plane strain assumption. Actually, you don't need to worry about the plane stress and plane strain. The only difference is elastic stiffness matrices. So that, and then last, we distinguished a CST element and cupo element. So that I think that which one is more suitable for the representative the result of the stress or strain values. But in this, after the finishing this lecture, you guys can easily think about the cupo is more can suggest more accurate result. However, it's not always correct. So sometimes the triangle element can suggest more accurate solution. So that this is a more advanced topic. So anyway, but in our 2D structural analysis, cupo element can suggest more accurate result. So this is the end of the lecture of the 2D structural analysis. Maybe next lecture I'm going to discuss about the numerical integration and the isoparametric technique for the numerical analysis. But after finishing those kind of topic, I'm going to discuss about the other physics phenomena. So this is the end of today lecture. So if you have any question, please send the email freely.